Okay. Good. So so last lecture we talked about the property of this propagator, which is defined to be x prime, which is also the same as phi x prime 0. Okay. So this object we discussed. So conceptually, it can be considered. Say I have two interpretations. So one is from here. So this is roughly can be heuristically interpreted as the transition amplitude for a particle from x to x prime. Okay, so heuristically, you can think of it, say, as the, say, if you have a point, say, if you have a space-time point x prime, have another point x, and then you ask what's the transition amplitude from x prime to x. Okay, so one way to interpret this object is that. And as I emphasize, this is only heuristically, because this does not really describe a generally localized state. It's only approximately localized state. Okay. And similarly, the second interpretation is the correlation function that it describes correlations of phi between, say, x, just correlations, describe correlations between the value of phi at x prime and the value of phi at x. Okay, so this is the interpretation most convenient, for example, from condensed matter perspective, if you phi, say, describe average spins. Okay, so similarly, the G malus, which is defined to be in the opposite order, also have two interpretations. So this is like a transition from x to x prime. Yeah. So if I draw x, if I still draw x that way, so it's like a transition amplitude like this. Okay, from x to x prime. Okay. So you can similarly interpret the other from the using this language. For example, this Feynman, which is theta g plus x prime plus x minus, and then this means that when t is greater than t prime, say if now let's take this to be the direction of time going up, and now if the x has a later time than x prime, and then describe the transition from x prime to x. Okay, but if the x prime has a larger time and x has a smaller time, and then describe the opposite direction from x to x prime. But in both cases, so you always go from the smaller time to bigger time. Okay. And so we often call this also GF the time-ordered correlation functions. So the GF is also called, so it's called the Feynman-Green functions. It's also called the time-ordered. Okay. Correlation function. Okay. And then we wrote down the expression. So we calculate the expression explicitly for G plus. And we also almost finished the expression for, similarly you can do retarded, etc. And also so any questions on this? Yes?
So on the P set, we showed that for the complex scalar field that I is 0 in that expression.
Yeah, yeah.
So what does that mean? There's no propagator for the...
Because of the charge conservation. And you cannot propagate from one particle to the other particle. So because phi, when it acts on the 0, generates, say, a particle. But when phi acts on the left, it actually generates the antiparticle. So a particle cannot become an antiparticle. Right, so only when phi and the phi dagger, and then it's from just the particle. Yeah. Other questions? Okay, good. So we also discussed so we wrote down this formula for R, A, F, say in coordinate space, say x prime, can be written as a Fourier transform I think it's k squared plus m squared. Let me just check the sign. I think it's I or minus I. Yeah, minus I. So, okay. And then this factor, then we mentioned that this factor actually has a pole. In the downstairs, this have the form omega square minus omega square plus omega k square. Okay, if you write it explicitly. And then this quantity becomes singular at singular at omega equal to plus minus omega k. Okay. And the singularity lies on the integration contour if we consider a complex omega plane. And so here one of the integral is the omega, and then the omega go along the real axis. So the integration go along the real axis, and here is minus omega k. Here is omega k. Okay, so you have singularity on the integration contour, and then different ways of going around the singularity then give you different choice of retarded and advanced and Feynman. Okay? And which one to choose based on which contour you should choose, whether you should go around, go above or go below the singularity, and depend on the prescription for each of them. Okay? So we discussed that for GR, which is proportional to theta, t minus t prime, then that means we should, so let me just draw the singularity. So that means you actually need to change your contour to go above the singularity, to go above the both singularity. Okay, so that will guarantee you to proportional to theta minus theta prime. When you do the integral, the omega integral using the contours, okay, using the contours. And similarly for GA, which is proportional to theta t prime t minus t prime, in order to guarantee that, then you have to take your contour to be below the singularity. Okay, to be below the singularity. So this is all omega, real omega axis. Okay. And for the Feynman, so the Feynman is half and half. So there's a theta t minus t prime part, there's a theta t prime minus t part. Okay, if you try to to check that, so we are not going into details there. Here I will leave you exercise for yourself. So if you want to satisfy that kind of condition, when t greater than t prime give you g plus, and when t smaller than t prime give you g minus, you find when you do the contour integration, you have to do the following way. So for this one, you go below. For this one, you go from up. Okay. You go up. And so that's the. And then there's another way, which is GF tilde, which is the opposite for GF in terms of time ordering. And then you will do the opposite way of here. Okay, so altogether, there are 4 different ways you can go around the singularity that give you 4 different kind of functions. Okay, they give you 4 different functions. So for those of you who are not familiar with complex analysis or the contour integrals, try to refresh yourself a little bit. Okay, because the complex analysis is definitely a very, very powerful tool. Okay, to be very familiar with it, it's very important. Okay, so it's annoying each time if you have to specify your contour like this. Okay, so if each time you have to specify a contour like this, it's not convenient. And then physicists developed a more convenient way to treat all of them in one shot. Okay. So instead of going around the contour like this, we just try to move the singularity. Okay, so we keep the contour to be fixed, but we slightly move the singularity. Okay, for example, for the retarded, this is the same if I just slightly move the singularity by tiny bit below the real axis. So if my integral contour is like this, then this is equivalent to that. Okay, if this is just tiny part, then this won't affect your answer. Okay, and similarly here, in this case, we just move both singularity above a little bit. And in this case, I move one singularity above, move one singularity down. So in which case, I don't have to change my contour, just slightly change my singularity. And this can be achieved by so-called epsilon prescription, so convenient, a convenient trick. Is in for example, in the retarded case, instead of this, so we always do the integral with the same contour. So we don't change the contour, but we slightly change the integration to be omega plus I epsilon square plus omega k squared. Okay? So the downstairs previously was minus omega square plus omega k square. But now I add a tiny, so epsilon is infinitesimal, is positive, and infinitesimal. Okay? So you see, by adding such a tiny piece to here, when you solve this singularity, so it's now omega plus I epsilon equal to plus minus omega. And then when you move the epsilon to the other side, and then the solution becomes minus I epsilon. Okay, and then because epsilon is positive, then this is slightly in the lower half plane. Okay, and similarly for the advanced, you just do a minus. Okay, and then both singularity will move up. Okay, and for the Feynman, so the trick is you can do the same thing. Yeah. Sorry, so still have ik. Okay, so this is the minus I. So I just do k squared plus m squared, the whole thing minus epsilon. okay, rather than change the omega and the whole thing minus I epsilon. Okay? And you can check yourself. When you solve the omega using this, just the whole thing minus I epsilon in this case. So for retarded and the advanced, you put it inside the omega square. But here you put outside, okay? And then you can check when you solve for omega, actually, you get this situation. One move up, a negative move up, and the positive move down. Okay, yes?
Can you outline like how I would convince myself, prove it to myself that these two pictures are equivalent, whether going, like moving, integrating with a contour that jumps up over or under these poles, or
Yeah, because from the contour point of view, from the contour integration point of view, it only matters, the precise shape of the contour is not important. Only matters whether what singularity it encloses. So as far as it encloses these two singularity, and then the story is the same. But since I change the singularity location only by epsilon, and in the end I will take this epsilon go to 0, and then the value will be the same. Yeah. Other questions? And so this is a very, very simple but very powerful trick. Okay, this makes things much more convenient, and when you do many manipulations. Okay. So that you don't have to constantly worry about the contour, the precise contour you take. Any other questions? Good. Good. So let me just give some final remarks. So this almost concludes our discussion of the free field theory. So let me just give some final remarks. So as I mentioned, that the G plus and the GR and the retarded have many applications. Say in condensed matter, so you deal with them all the time. And this Feynman propagator, it's we will see it plays a very important role. In next chapter, which we will start in the next few minutes. Okay, so the JF will play a very important role. Okay, and so in addition to this 2-point function, so these are the correlation function of 2 points. Okay, just the x and x prime. You can in principle consider, say, more general correlation functions. Say you can consider or in arbitrary state. Okay. Say for example, you can just consider some state psi, and then you can consider phi x1, phi x2, say phi xn. Okay. So this is like some endpoint function. Yeah, what's normally called endpoint function, some general state psi. Okay, psi does not have to be the vacuum. But since so general state, remember general state psi can all be built from A and A dagger, and the phi can also be written in terms of A and A dagger. So if you give me a state, so I can in principle calculate this for any correlation function. Okay, so this theory is fully solved. And no matter what you want me to compute, using what we have developed so far, you can now all compute them. Okay, so this theory, everything is computable. And so now let me just mention one simple fact regarding the vacuum correlation function. So let's consider endpoint function in the vacuum. Okay, and then you can easily convince yourself. Okay, you can easily convince yourself this factorize into sums of product of 2-point functions. Okay. So why? So this is simple because A and A dagger, they have to be paired. Because the any A dagger creates something out of 0, have to be annihilated by A somewhere later. Okay. So that means all the A and A dagger has to be paired, and then that means that they have to reduce to all the proform functions. Okay. So you can check explicitly. So for example, the simplest is the 4-point function. So if you consider phi x, okay, so you can easily convince yourself that the A dagger, when A dagger of this create on this, and then that can be, say, annihilated by any of them, okay, and so you can have, say, and similarly, A dagger created by this one have to be annihilated by some later. So you have to always pair them. Okay, so you can show that this just reduced to all possible pairings. So you can pair 3 and 4, or pair 1 and 4, and 2 and 3, or 1 and 3, and 2 and 4. Okay, you just write down all possible pairings. Okay, just write down all possible pairings. So essentially, so in free theory, so in this free theory, any point functions in the vacuum, they just reduce to the 2-point function. If you know the 2-point function, you know everything. Okay, you know everything. So this I will give you as an exercise to check yourself. And the final remark is related to the problem 3, I think, in your P set. Okay. So in addition to phi, we can also consider more complicated operators. Okay. Can consider, say, so-called composite operators. Means that we take the product of phi all with its momentum. Okay, so we can have, say, we can consider phi square, phi cube, say the Hamiltonian density, the stress tensor. So these are all involving some product of phis, okay, or is canonical momentum. And so these are normally called composite operators. And as you should have learned from your PSAT problem 3, that those operators often are not well defined, because when you multiply them at the same point, you will get singularities. Okay, you will get singular behavior. You will get singular behavior, and we need to renormalize them, etc. Okay, and so such kind of divergent behavior is generic in quantum field theory, and one of the most important part of quantum field theory is to find sensible ways to renormalize those emergent divergent quantities in the physically sensible way. Okay. And the problem 3, and it's the first example I encounter. And later, when we deal with interacting series, there are more complicated examples, etc. Okay. So do you have any questions? Yes?
So I'm a bit confused on how to interpret this endpoint correlation function because, like, for the 2-point, we have this heuristic transition amplitude picture.
Right.
But how do you interpret this, especially with, like, theories where it's not a free scalar field where you can decompose them like this?
Right.
Where phi can be expressed in terms of ladder operator.
Yeah, yeah. So just heuristically, you can imagine, these correlations as, say, you make measurement at n different points, and you study some kind of joint amplitude of them. Yeah, so this is one way to interpret this quantity.
Measure of, like, the value of the field?
Yeah, yeah. For example, if you imagine they are spin operators, and say phi denotes some kind of spin, and then you can imagine you measure them at n different space-time points, and you look for their correlations. Yeah, so this is the one example. But later we will actually almost see immediately, just today. I think we will reach there. And you will see this actually is related to the scattering amplitudes when we talk about interacting series. Yeah. Other questions? Okay, good. So try to enjoy the problem 3 in your PSAT, and after doing it, really read the problem again. Okay, read the problem again. And try to that problem contains the things which just the simplest situation for the divergences you will see in quantum field theory, and to be prepared for that. Is important. Yeah, even though we will not directly use the result of the problem 3 in the immediate future, but I think it's important as part of your education to get used to the infinities and the divergences in quantum field theory. Okay. Good. Other questions? Yes?
So I guess over here, everything on the left-hand side is in terms of these Green's functions, which could have been solved classically, like without doing any quantization. So is there a reason why, like the correlator in the quantized field theory is the same as like the correlator in the classical?
Yeah, just because it's a very simple. This is a very simple theory. Yeah. But even in this case, it's actually it depends on how you interpret the behavior of those functions. Even though this form, you might say, oh, maybe we could anticipate this. Say if you have say Gaussian statistical system, and you will anticipate this. Just say you only have Gaussian correlations and nothing else. But the specific form of the functions, they do encode quantum physics. And even though this factorized form is like in say like in the Gaussian statistical theory. Yeah. Good. Okay, so far we discussed the simplest free theory, just a theory of free scalar particles. Okay, they don't have spin. They have spin 0, so they don't have any space-time component, and they have some mass. Okay, relativistic particles. And later we will talk about electrons, which have spin half, and talk about photons, which have spin 1. Okay, and before talking about them, let's talk a little bit about interactions, because so far this theory is absolutely boring. Okay, so even though this theory illustrates this very important conceptual point that somehow when you quantize the fields, you can get particles. Okay, you can get arbitrary number of particles. It's a connection between the field and the particles. Okay, but just in terms of theory of particles, this theory is absolutely boring. Okay, there's nothing. The particles don't do anything. They just go straight. Okay, just Newton's first law. Okay, they just go straight like Newton's first law. And so now let's try to add a little bit fun to introduce a little bit interactions. Okay, and you will see that when you introduce a little bit interactions, the story becomes much richer. Okay. So now let's talk about interactions. It turns out to describe interactions, a very powerful approach is the path integral. Okay, so we will also discuss the path integral. So we will use the path integral approach to describe how to treat interactions. Okay. And yeah, so first, let's just say a few words about some general remark on interacting series. Okay. So previously, we considered a series with a Lagrangian density of the following form. And we find it's a free particle. It's a series of free particles. And now we can easily make this series to be of interacting particles if we just add some higher order powers. Okay, so for example, one of the simplest power is the 5 to the power 4. Okay. So yeah, you can also add the power 5 to the power 3, but 5 to the power 3 is a little bit sick. It's because the 5 cube is not don't have a definite sign. Don't have a definite sign. And so so 5 cube series does not have a well-defined energy. Okay, so your energy can go arbitrarily active, and so this is the simplest the interacting series with a well-defined, say, energy. Okay. So, and we will write this as L0, which is the free series part, which we considered, and then the interacting part. Okay, this lambda factorial 5/4. And so this lambda, essentially, heuristically, this lambda should characterize the importance of this term. So if lambda goes to 0, of course, then this term go away, and then this term is not important. And when lambda become bigger, then this term become more and more important. And so we call the lambda to be the coupling, okay, which characterizes the importance of this term. Okay. So now first let's follow what we were doing before for the general quantization procedure. We try to write down the classical equation motion, and then we quantize, and then we solve the most general classical equations, the most general solutions for the classical equations, and then we promote those solutions to operators, right? Yeah. So let's try to do this one. So now when you write down equation motion, so equation motion is very simple. You just get partial square phi, m square phi. So this is the free series part. And now you have a nonlinear part, the cube. Okay? So now you have a nonlinear equation. And so who can solve this equation? Any volunteers? It turns out actually this equation, nobody has been able to solve it so far. Okay? So we don't know how to solve it. Okay? And so our previous strategy, even though sounds very powerful, and immediately breaks down. Okay? Because of rely on, you can actually find the solutions to this equation motion. Okay? And yeah, so we don't know how to solve this. But heuristically, you can imagine that this indeed should be a series of interacting particles. Because previously, when you don't have this term, you just have a linear equation, then the phi is not doing anything. Okay, now you have a phi cube term. So that means that different phi's can now doing something together. Okay, so when different phi's doing something together, by definition, that's called interactions. Okay, and that's called interactions. And so just heuristically, this should already give you a series of interacting particles. Okay. So we will talk about how to treat such a theory. Since this cannot be solved exactly, we can only try to solve it approximately. Okay. So the only way we know how to solve it approximately so far is you imagine the lambda is small, and then you just expand the lambda perturbatively. Okay, just treat the lambda as a small parameter. You just expand in lambda. And so I will outline this procedure in a little bit. Okay, but before that, let me just make some general remarks which apply to general interacting series, which this is just one of the examples. Okay. So actually figuring out interactions from experiments is actually one of the main tasks of the particle physics and many areas of condensed matter physics. Okay, and so for example, we build LHC at the CERN, and you collide these protons together, billions of dollars. The whole purpose is to figure out the interactions between the particles, between the elementary particles, and to verify them, etc. Okay. And similarly with many condensed matter experiments. So now I ask you a simple question. So what's the most powerful way experimentally to probe the interactions between particles? What is the word to describe that kind of experiment? What? Yeah, scattering. So you should already have learned this in quantum mechanics. So scattering is the key thing, okay? So that's essentially the universal approach we have been using for more than 100 years, starting from Rutherford, okay, who first shoot the helium atom at the first shooting electrons at the helium atom. Okay, no. Shoot the alpha particles at atoms, and so the scattering, and then so you have Rutherford. And then you have the so-called deep elastic scattering, DIS, which figured out that the proton actually have substructure, which leads to the discovery of quarks. Okay, and actually MIT played a key role. Friedman and Kendall in the DIS experiment, which figured out the structure, which discovered that the quarks were. They played a key role in that. So, and still, many interactions and the particles were discovered this way. Okay, and so the basic idea of scattering so essentially, it's very simple. You just collide a bunch of particles okay, and just examine the outcome. Okay, so from the outcome, you try to deduce what are the interactions between those particles. Okay, so that's what the experiment, scattering experiment about. Okay, so from here, you deduce the interaction, which has always been very successful. Okay, so in condensed matter, you have neutron scattering, etc. Okay, X-ray, you can use X-ray and neutrons to shine on your samples. And one of the most important observables for the scattering experiment is what? Again, this is a simple question of quantum mechanics. Sorry? No, momentum is not that. The cross-section is close, but there's more fancy words.
Differential cross-section?
That's fancier, but not fancy enough. It's called the S matrix.
No, I said S matrix, but I didn't say it loud enough.
Oh, okay. Yeah, just be braver next time. So one of the key elements, so one of the key observables for scattering is a so-called S matrix. Okay. So define S matrix. We need a little bit of mathematical idealization. Okay, just as always in physics. So the mathematical idealization in order to define S matrix is the following. So at t equal to infinity, t equal to minus infinity, prepare initial state initial state, maybe the initial state as localized say wave packet infinitely far apart. So this is the mathematical idealization part. Okay, we want them to be infinitely far apart. And then, but you aim them. Okay, so you prepare them spatially infinitely far apart, but you aim them, you prepare their initial momentum so that they can come together at some point. Okay, you aim them. And then they will come together at some point, and then they will scatter, they will interact with each other, and then they will form some final product. And then the final product will then run away from each other. Okay, they all have velocity momentum, they will run away. And then you just wait until those products are far apart, then you measure them. Okay, so that mathematically this is called as t equal infinity. Yeah, of course, t equal to plus minus infinities are also mathematical idealization. And the final particles are also far apart. Again, infinitely far apart because they are all relativistic particles and they all move. And even with slightly momentum difference, eventually they will be infinite. If you wait a long enough time, then there will be. So these far apart are very important, these two. Because this means we can neglect the interactions as t goes to plus minus infinity. Okay, so with this setup, and then at t equal to plus minus infinity, they are very far away, and then you can neglect the interactions. This is important, then we can identify each particle. Because when they are together, they're all interacting with each other. It's not easy to cleanly identify each particles and discuss their property. Okay, and so now we can neglect the interactions. So the initial and final states are then collection of free particles. Okay. So, and it can be described by free theory. So this is very important because remember we cannot solve this kind of interacting theory exactly. Okay, so now but we can reliably, almost to infinitely accuracy, to talk about the initial state and the final states. Okay, and we can talk about them as precisely as we can, as far as we go to t plus going to plus minus infinity. Yes. Yeah, just in principle, any nonlinear term will lead to interactions. Yeah, the intuition is that anything beyond the linear level, you will have different phi's coming together. So whether it's phi cube there, or phi fourths, or higher powers, or exponentials. Just just anything which is not linear, phi's have to do something with each other, and then that just means interaction. Yeah. Yes. Sorry, say it again?
So we had
Yeah, this does not give you interactions because this just, remember, when you do equation motion, that still give you a linear term.
Oh,
linear term just give you a mass. Yeah. Right. Yeah, this is, in the Lagrangian, the quadratic term, a free term, so things above the quadratic term give you the interactions. Yeah, yes? Yeah. Here you cannot translate. Here I'm just giving you the intuition that somehow when you add such kind of nonlinear term, that should lead to some kind of interactions. But to understand what precisely kind of interactions, you have to look at physical observables. So that's why we need to look at the S matrix. Even for this theory, we want to say, suppose we have this theory, but in real life, what does this? How do we see in the real experiment? If this theory can be realized in the real experiment, what it looks like. And the only way to see it is through this S matrix. Yeah. And so we through S matrix, and then, we can deduce back. Good? Okay, good. So this is important because this makes sure that even when we are unable to solve this theory exactly, we can still talk about initial and final state exactly. Okay? At least we can define our problem precisely. So let's denote the collection of initial particles to be alpha, the momentum of initial particles. So essentially, this characterizes your initial state. Okay? And because here we're talking about scalar particles, they don't have spin, so the momentum are their only quantum numbers. And say I use beta to describe their final momentum. I call them P1 prime, say Pn. So the initial number of particles and final number of particles don't have to be the same. Okay. And then the scattering process is just to go from alpha to beta. Okay, you start a bunch of particles at the t equal to minus infinity with those momentum, and then at t plus infinity you observe some other particles with those momentum. Okay, and then we want to understand the transition amplitude between them. So that's what the experiment measures. Okay, and from here, of course, you get the cross section, etc. But this is a more fundamental object. So to write this precisely, so essentially we are looking at, say, in the Heisenberg picture, this is my final state, and I look at the evolution from minus infinity to plus infinity, starts from initial state alpha. So this is the evolution operator of of your quantum system. Okay. And so sometimes we also write this as the, so this is in the Schrodinger picture, and in the Heisenberg picture, we write it as this. So now this means that this is the state defined at minus infinity. This is the state that defined at plus infinity. Okay, so this is the notation in the Heisenberg picture, and this is the notation in the Schrodinger picture. Okay. So this object. So this object we often denote. So you can vary, you can run alpha and beta over all possible initial states and all possible final states, and then that form a big matrix. In fact, infinite times infinite matrix. Okay, and so this is our S matrix. So essentially, all your secret of interactions are encoded in here. Okay. Yes. Yeah, because you can. Yeah, so so this is, so you have a value for any choice of alpha and beta, right? And so any choice of alpha and beta is one matrix element, and but you have infinite possible choice of initial momentum. Yeah, you can have arbitrary number of particles, you can have arbitrary momentum, and similarly for in principle for the final states. Yeah, here, for this particular problem, it's one kind of particle, but this definition is very general. This is a very good question. It doesn't matter whether you have one kind particle, a two kind particle, even infinite number of particles. Yeah, infinite species of particles. So here, even for one kind particle, I have infinite possible choices. Because I have infinite possible choice of all those momentums. I can choose k equal to 1, 2, 3 to infinity, and also the value of those k can all change. P can change. So yeah, so this is an infinite times infinite matrix. Okay. Okay, so essentially this S, this is essentially just a matrix element of this evolution operator. Okay, essentially just the matrix element of the evolution operator. You can see it from here explicitly. Okay, from minus infinity to plus infinity. Okay. Good. So so it's convenient. So let me just say a few things about the S matrix. So it's convenient. So when interaction is weak, so when the interaction is weak, you can imagine most of the time the particles, they don't interact with each other, okay? So when you do the scattering, you put a bunch of particles scattering. If the interaction is very weak, then they don't actually interact very much, okay? So we expect, so when the S equal to identity, then that means there's no interaction at all. Okay, for free theory, it would be just identity. Okay, so now if you think that the interaction is weak, and then it's convenient, we write the S matrix in the following form, IT. Okay, and this includes the interaction part. Okay, captures interaction effect. Okay. Good. And by definition, yeah. Any questions on this? Yes?
So I was interpreting the elements of the S matrix as sort of like the probability to end up in a certain state from an initial state.
Yeah, it's S matrix is the amplitude. The probability you have to square it.
Oh, yes.
Yeah.
But then why does it make sense that if it's a weak interaction, that it would, like, as the limit goes to like no interaction, the S matrix would be 1, or the identity?
Sorry, say it again?
So why do we say that for weak interactions it's the identity?
Yeah, if there's no interaction, it will be identity.
But why does that make sense? Because that's just saying like the amplitude is 1 to end up in a certain state?
Yeah, just you always go back to it, so the state does not change. Y means that the delta means delta alpha beta. Just alpha must equal to beta.
Oh, I see.
Yeah, the Y means just delta alpha beta, right? So means the alpha equal to beta. Yeah. Yes?
Ask Hermitian matrix.
Yeah, we will talk about that. It's not Hermitian, it's unitary. Yeah. Yes?
Does the phase of the entries in S carry any physical consequences?
Yeah, that's a good question. So if you consider particular amplitude, when you square it, of course, the phase don't. But in principle, you can design the different, you can define experiments and the different things they can interfere. Yeah, yeah. So in principle, they contain physical information. Yeah. Yes.
Why is this entry complex?
Oh, just convenience. Yeah, just for convenience. Yeah.
Yeah, if alpha was a particle at like minus x infinity and beta was the same particle at like plus x infinity, would that be captured by S just being
Sorry, say it again.
like if my alpha to beta was just particle here goes to particle there, is that captured by S equals 1?
Yeah, yeah, yeah. Just say if the say in the free theory, if you start with a bunch of particles p1, pk, then you end with the same p1, pk. Yeah, yeah. Okay. So due to translation symmetry, so we expect energy momentum conservation. Okay, so yeah, so this, if you write it in terms of the component rotation, so this is delta beta alpha plus I t beta alpha. Okay, and I just purely convention. Okay, I is purely convention, just for convenience. So so due to the momentum conservation, so this corresponding to the interaction part. So in this part, you expect alpha not equal to beta, okay, because you have interactions. But the total momentum must be conserved, okay? So the sum of here must be the sum of here, okay? Just the total momentum must be conserved. So that means this thing must contain a delta function between the total initial momentum and the total final momentum, okay? And so we can just convenient to extract to separate that delta function. Okay, so convenient to write it beta alpha equal to I. You separate out this delta function because we know this delta function must be there. So p alpha minus p beta. So p alpha and p beta means total momentum. Okay, for alpha and beta, and then you have m alpha beta. So this is the non-trivial part. So this part is trivial. You expect from kinematics. Okay, and so this m alpha beta is called the scattering amplitude. Okay. So now some properties of the S matrix. Because you see that S matrix is essentially just a matrix element, essentially just the matrix of the U. And the U is a unitary matrix because it's an evolution operator. Okay, so that means that the that means that the S matrix is unitary. Since U, this is a unitary operator, so that means that S is a unitary, okay, matrix. Okay. Also, you can show, so I'm a little bit running out of time because today we have to end at 5:40, and so for any symmetry of the Hamiltonian, that means that if you have some Q, if you have some, say, some unitary operator which commute with the Hamiltonian, okay, Okay, so remember all the symmetries, their action are generated by unitary operators. Okay, so suppose we have some unitary which commute with the Hamiltonian. Then you can easily show yourself. So this is the I leave this exercise to yourself. So lambda is a unit operator generating some symmetries for some symmetries. Okay, so for example, for the Lorentz transformation would be like this I omega m, which you have done in your homework. And then it will satisfy. Then when you act initial state and final state by this lambda, and then the matrix should be the same. Okay. So you can easily prove this by using the commute. Okay. Yes.
Is another equivalent way of saying that, like S and lambda also commute?
No. They don't. Yeah, that's the statement, right? This is a statement. So S are matrix elements. So it's a statement that the lambda commute with U.
Okay.
Yeah, lambda commute with U, and S is the matrix element of U.
Oh, okay.
Yeah. Okay, so this is the key object we want to calculate in the interacting theory. So now without proof, okay, because the proof requires something going beyond what we discussed so far. So let me just quote this LSZ theorem, which says that the M alpha beta, this scattering amplitude, can be obtained so we will discuss how you obtain it later from such a correlation functions, time-ordered correlation functions. So this omega is the vacuum of the full interacting theory. Okay, so this is the vacuum. So I write omega to distinguish it from 0, which is the free theory we discussed earlier. Okay. And so this time ordering means that you order the operator according to their time. So whichever time is bigger sits earlier. Okay. So this is the object, key object. If you want to calculate M alpha beta, you have to calculate this object first. Okay. And so I will stop here. And so next time we will say a few more words about how the general approach to treat this kind of theory. And then we will start talking about the path integral. So have people studied path integral before? So you all expert of path integral or not quite?
Heard of it.
Okay. Yeah, so I will review the path integral. I will actually introduce the path integral from scratch, but I will do it a little bit faster than ordinary quantum mechanical class. And even for people who have not seen it before, I think you should be able to follow with a little bit effort after the class. Okay.